for marginally outer trapped surfaces. Okay, so the idea is if you have a trapped surface, then that should be contained in some enclosing surface which is actually marginally trapped. Because if you move far out, of course, surfaces are untrapped, right? They're convex, and so they're certainly not going to be trapped. And so you would expect to have a kind of envelope of the trapped region which would be marginally trapped, marginally out of trapped. So that's called a MOTS. Okay, and so in particular, so this is actually an interesting geometric condition on surfaces which generalizes the theory of minimal surfaces in a very interesting way. And in particular, there are a lot of similarities. So there's a stability condition for MOTS. So I talked about stable minimal surfaces yesterday. There's a stability condition for MOTS as well, although it has to be formulated differently because the MOTS equation is not variational. So you can't produce MOTS by minimizing anything. And so you have to use other ideas for doing it, but people have developed a fairly sophisticated theory of doing that by now. Actually, it mostly starts in my paper in space-time energy theory. Okay, so, right. But there's a notion of stability, which I want to focus on. And stability for the minimal case just means the second variation is non-negative, means locally minimized. For MOTS, the stability means that there's a family of surfaces that contains our MOTS. So in this picture, the MOTS is this is the Schwarzschild horizon. So the MOTS is the throat there, and let's say infinity is points upward here in the picture. Then if I look at just the family of constant curvature spheres there, if I go behind the horizon, then those surfaces are outer trapped. Those are strictly outer trapped because when I move outward, they decrease, right? Whereas if I go beyond the horizon, they're strictly untrapped. And so that's an example of a stable MOTS. So if there's any family of surfaces which go from strictly trapped to strictly untrapped, then that MOTS is stable, called stable. And again, stable MOTS satisfy conditions very analogous to stable vector surfaces. Okay, and so let me just say that, and since I'm going to be a little short on time, let me say that the constraint equations impose very strong conditions on stable MOTS. So it's the constraint equations together with the dominant energy condition are some kind of positivity condition on the curvature of the manifold, and they very much interact with the stability of MOTS. In fact, they force most MOTS to be unstable. And so if you have a stable MOTS, then that's a very special thing in an initial data set. And so, as Penrose theorem suggests, stable MOTS produces a singularity, but just generally most MOTS will be unstable. And for example, Hawking's theorem on the topology of a stationary black hole is related to the fact that a stable MOTS in the three-dimensional case, that is a surface in R3, is necessarily topologically a sphere, has positive order vectors. And that's a consequence of the stability topology. Okay, and so actually, Greg Galloway and I generalized that to the higher dimensional case as well. And so a good analog to think of is the behavior of geodesics on the surface of positive curvature. So the positivity of the curvature causes geodesics to be unstable in general. So if you were on a sphere, any geodesic which is longer than halfway around is going to be unstable. So you have very strong restrictions on stable geodesics, and it's the same kind of idea for the MOTS case. Okay, and so I want to just close part two by talking about a question. So it turns out that in the proof of the positive energy theorem, there's a slightly different kind of MOTS that comes up. Namely, the proof involves, so the mean curvature proof, the original proof involves looking at MOTS which are not compact, but which are asymptotically planar. Okay, so you can imagine you might have so this is an asymptotically flat spacetime, you might have a MOTS which converges, sigma 2 or sigma n, which converges at infinity to a plane. So you can ask, well, what can you say about stable MOTS that converge to a plane at infinity? And it turns out In fact, an important step in the proof of the positive energy theorem is that such MOTS don't exist under the condition that the dominant energy condition holds strictly. Okay, and so I probably don't have time to write this down, but the stability inequality involves, it involves terms, so the stability inequality involves terms like this. So let me just do the P equals 0 case, which is an analogous result for the MOTS case. And so there's a term which is the scalar curvature, so it's just a constant times mu, and then there's a term which is minus the Gauss curvature sigma, and then there's a positive term which is the second term of the form squared. So this is the eigenvalue condition which corresponds to stability sigma. Okay, and so in particular we're assuming the dominant energy condition, so this is non-negative, mu is non-negative. And then basically the idea is in 2 dimensions, if you're asymptotically planar, you can basically take phi to be 1 here. You can send phi to 1 and make the right-hand side go to 0, 2 dimensions, special 2-dimensional construction. And then you can end up proving that the integral, so sending phi to 1, you can end up proving that the integral of minus k sigma, and let's throw away that term, so that's a positive term, you end up proving that this is less than or equal to 0. In fact, it would be strictly less than 0 if mu were positive. If we had strict stability, then if we had strict dominant energy condition, then this would be strictly less than 0. And that's actually a contradiction because any non-compact surface always has non-positive Euler characteristic, right? If you take a surface which is, so a compact surface, of course, could be positive, could be, it could be, sorry. So I would get, sorry, when I convert to the Euler characteristic, I get that the Euler characteristic of sigma is strictly bigger than 1. So any non-compact surface has Euler characteristic less than or equal to 1. The disk has Euler characteristic 1, and all the others are smaller. Okay, so in particular, if we had strict, so there's an issue here about the borderline case. So if we had the strict dominant energy condition satisfied, we could actually show that there are no asymptotically planar stable minimal surfaces or stable MOTS in the general case. And so the question that we ask, the question that I ask my student actually, is whether you actually need the strictness in this inequality. It's actually a little bit awkward to do the strictness, especially in the space-time case. And so, the question is it possible for a non-trivial initial data set to contain an asymptotically planar stable MOTS? It turns out to lead to some interesting questions. So the idea is roughly, so in the borderline case, although you can't prove it doesn't exist, you can prove that the data is pretty much flat near the MOTS, right? And so it leads to the question of how flat an initial data set can be. So the MOTS would be like a plane at infinity, and sort of near that plane the data is trivial. And the question is, could it be non-trivial elsewhere? So for example, could you have a space-time or an initial data set which is trivial in half space and non-trivial elsewhere, asymptotically flat? So that would, and it turns out that in fact they do exist, and so let me explain that. So this, I'm going to talk about a localization here for solutions. And so as I tried to describe, the energy and linear momentum exist under these very weak assumptions. Q is bigger than n minus 2 over 2. Okay, and so actually it's an important issue to understand the asymptotic behavior of solutions of the constraint equations, because they have a strong impact on the evolution, for the evolution problems before. And in particular, people usually, if you look at the literature in relativity, people normally assume that the asymptotics for the data, that is for G and P, are, to leading order, the asymptotics of a hypersurface in Schwarzschild, right? So if you look at the Schwarzschild spacetime, then of course you can find one with any energy you like, it's a parameter, and you can also impose linear momentum by doing a boost. So in the space-time, you can look at the graph of the linear function. And what happens when you do that is some of the energy gets transferred to linear momentum. Or some of the mass gets transferred to linear momentum. You can achieve any energy momentum vector by a slice in the Schwarzschild spacetime. So people often assume that the asymptotic should be like that. In fact, that's really justified in a strong way by a construction due to Corvino and also Crucial and Delay has a description of it. So in fact, we showed that you can take any initial data set you like with just reasonable asymptotics, and you can keep it the same in a very big set, and you can make it exactly a slice in, well, not Schwarzschild. You also have to put in angular momentum, so you need what's called the Kerr solution. So there's a little larger class of solutions that I will describe here. But it tells you that in fact you can always construct data. In fact, you can perturb any given data with good asymptotics, with reasonable asymptotics, to one which is exactly of this type. So it's known explicitly at infinity. It's a boosted slice of actually the Kerr, which is so the only difference. So the Kerr is a generalization of Schwarzschild to rotating black holes. So there's an angular momentum parameter. And that's a theorem that says that this sort of idea that people had is justified in the sense that you can it's really enough to consider data like that in general. Okay, and so let me point out a further consequence of positive energy is relevant to our question. So remember we're asking the question of how flat an initial data set could be without being actually trivial. And so the positive energy theorem has a consequence, of course. It's so I should have said So first of all, I should have said that the positive energy theorem obviously implies that you don't have any data with compact support. Right? You can't be trivial outside the compact set, or the energy be zero and you'd be trivial. But now there's a little more precise form of that, which is actually quite easy to prove, and I think I'll have to skip the proof because I want to describe the theorem. So actually, if you assume sort of the Schwarzschild type asymptotics, then in fact, if you look at the set of points where the Ricci curvature is non-zero, okay, so you can take your metric G and you have an open set of points where the Ricci is non-zero, so the metric is definitely not flat. In fact, it has some Ricci curvature. So that open set, of course, it has to extend to infinity because the space-time is non-trivial. In fact, it has to subtend a sort of angle at infinity. So that set has to be quite large. In infinity, it has to include a fixed fraction of the sphere at infinity. So the set has to be something like that. So when I cut it with a large sphere, it has to be a good fraction. So this is a set U, and say the solution might be trivial outside U, it might be flat or Ricci flat anyway. So the statement is that if the space-time if the data is non-trivial, then in fact the lim int of the ratio of the volume inside U on the sphere to the volume of the sphere is strictly positive. So that's a consequence of positive energy. So it's telling you that unless the space-time is trivial, there's quite a lot of curvature out near infinity. So the set has to extend quite large. And in fact, the proof is pretty straightforward. The main point actually is a slightly different formula for the energy in terms of the Ricci curvature, which I guess I don't have time to explain. But once you have that, you can see that just using the fact that the energy is positive, for sigma sufficiently large, you get that this integral in absolute value is large, and using the bounds, the decay on the metric, you immediately get the lower bound of that quantity. And so in particular, if you ask the question, how flat can a solution be, then the set of points where the curvature is non-zero has to at least include sort of the cone angle and positive cone angle. Okay, and what we showed is that condition is quite sharp. Namely, if we start with an asymptotically flat manifold, we assume the curvature decay. So I need a little bit more. I need 2 plus alpha decay for this theorem. I assume it decays like x to the minus q, so q is bigger than n minus 2 over 2. That makes the energy exist. and less than or equal to n minus 2 for some alpha, then what we show is that you can make the following construction. You can take, so let me just think about this first for the Planck's metric case, where you just have metrics of zero curvature. So what you can do is you can take any cone angle you like. So we have our initial data set. So our initial data set is very non-trivial in some. This is sort of the compact region, and then outside that compact region, it falls off in a nice way to infinity. And so what we can do is we can take a point Q, which is far out, and we can take a cone of arbitrary angle. So let's call the angle here theta 1. And then we can take a theta 2, which is a little larger angle. Theta 2, which is a bit larger. And then what we can do is we can construct a new solution which is identical with the one we started with here, and which transitions in this conical region to the Euclidean metric. So out here our solution G bar is identically Euclidean. So it's a kind of localization in a cone of these solutions. The only catch, so it turns out this construction works, except there's one caveat that I want to make, and that is that it doesn't work at the optimal decay, that is n minus 2 over 2. So in order to do that, you have to weaken the decay a little bit in the transition region. So you need Q strictly less than n minus 2 in order to do that. Okay, so we know that you can't sort of approximate things by compactly supported ones, but what this says is that you can approximate them by solutions which are supported in cones of arbitrarily small angle. And so in particular, right, but as I said, it doesn't work at decay n minus 2, so you need Q to be strictly less in order to do that. So you have to give up a little bit of decay in the region. Okay, and so I just want to describe a little about and ask some general questions. Okay, so the first question to ask here is, this looks impossible, because if I started with a solution that's sort of isotropic near infinity, that means it's like a Schwarzschild solution, it's rotationally symmetric up the leading order, then of course the energy is evenly distributed around the sphere of infinity. So if I took the energy in a small cone, no matter where the center of the cone is, that will be a very small fraction of the energy I started with. Right? And so on the other hand, I'm claiming that these things have energy almost identical with the energy we started with, so we don't lose any energy when we do this. Okay, and so the explanation for that is that the transition region actually accounts for most of the energy of the solution. So the metric has to be quite complicated in the transition region, and in particular, that justifies the condition that you need to assume that you can't impose too much decay in the transition region. And so remember that term, the term that gives you the energy, it's a term that involves a derivative of the metric. And so if that derivative were bounded by r to the 1 minus n, then there would be a very small contribution there. So the fact that the decay is a little weaker allows the possibility of a lot of energy there. Okay, and so that's actually what happens in this approximation. Okay, and so in particular, coming back to our basic question, which I used to motivate this, what's true for stable surfaces? Well, it turns out it's not true, right? You can have non-trivial initial data sets which are actually trivial in a half space. So in particular, there are lots of stable knots in there which are just Euclidean planes in the half space. Okay, so it's generally not true. However, again, the question is still open if you assume x to the 2 minus n decay. So if you assume decay at the Schwarzschild rate, then it's still not clear. In fact, my student, the first thing he did is he was able to rule out stable minimal surfaces of knots in the case where you assume the metric is a boosted slice in Schwarzschild up the leading order. So it turns out in that case, if you have sort of more isotropic asymptotics, then in fact it can happen. You cannot have a stable minimal surface of knots. Okay. And so let me mention an application of this, which I think is sort of interesting. So one thing you can do with this construction is you can sort of superpose solutions in the Einstein equations. So what I can do is I can take, let's say I have two different asymptotically flat initial data sets. Then of course I don't have any direct way to add them up to produce a solution which combines those two. However, what I can do is I can take one of them and I can approximate it by a solution supported in a small cone, and then I can take the other one and approximate it by a solution supported in another cone, and then I can put the cones together. So I get solution 1 here, and solution 2 there. And then of course, they're both Euclidean outside the union of the two cones, and so that those fit together to form a nice smooth, I can make these solutions as smooth as I want, initial data set, and they have disjoint support, so I can add them up, I get those two. And then the total energy of that and linear momentum will just be the sum of the two, because the contributions in the exterior of the cones will be 0. The data is trivial there. And so what I get is a new solution whose energy is the sum of the two energies, whose linear momentum is the sum of the linear momenta, and which agree on arbitrarily large sets with the ones I started with. So it gives a very kind of, I think, appealing construction of what are called n-body solutions. So actually, I should say that quite recently, in the last year or two, there's a construction using the Corvino type construction that to do this also, to put together solutions using the sort of approximation by solutions that are equal to a curve slice near infinity. And so, right, and so that's a nice application of the work. And so we mentioned two open problems. I'll say just a little bit about the proof. I won't have time to say very much time here, but so let me just mention the two open problems. So first of all, the question of whether this can happen with Schwarzschild decays, that is with decay of the order x to the 2 minus n, is still not known. This construction definitely will not be able to produce solutions that decay at that rate. And then they're also, so we haven't actually done it. We think we can also do the general space-time case. So far we just have written up the time-symmetric case. But there will be a similar localization here and there. But I think the second problem is very interesting. So in the time-symmetric case, of course, there's stability, but a much stronger condition is area minimizing. And so actually, in the proof of the positive mass theorem, we actually looked at area minimizing surfaces. And so in fact, our surfaces were a little more than stable. And so it's not. So the question of whether there could be an area minimizing asymptotically planar surface is also not at all clear. So in other words, in these solutions, there are these localized solutions. There are these planes out here that are locally minimizing, but it might happen that when you look at the plateau problem, that is, you look at arbitrary competitors, there might be a smaller surface that moves into the curved region. And that I don't know. I mean, it actually, I think, plausibly could happen. So that's another question. And let me just in the last few minutes say just a little bit about future proof. I at least want to explain how the decay assumption comes in. First of all, there's a more precise description for those of you who like weighted cellulose spaces and stuff. There's a more precise description with the theorem. So there's a version in Holder spaces. So you can, if you assume G minus the Euclidean metric. So if we assume in the interior it has L derivatives, L alpha derivatives, so alpha is the Holder coefficient, and it decays. So this means it decays like x to the minus q, and there are k alpha derivatives that decay. And then assuming q is in that range and L is bigger than it decays at least 2, then in fact you can do this construction precisely in this space. So you can keep the same decay at infinity, the same number of derivatives decaying, and you can also keep whatever smoothness you have in the interior when you do it. And then there's also a version in weighted Sobolev spaces. And again, emphasize. So there are other ways, of course, of codifying the fact that a function decays. Instead of pointwise, you can assume Sobolev decay. And the theory works also in that setting. Let's skip that time. And so the outline of the proof is fairly direct. So the idea is just to construct an approximate solution. So you just sort of patch together the metric G inside with the Euclidean metric outside. So I've called that metric G tilde. So you have to choose. You have to be a little careful how you patch it. So you choose the patching function to be a function of the angle. So you can't use the distance of the boundary. So because the angle function has appropriate decay when you differentiate it. So it's important to use a function of the angle. So chi is just a cutoff function, which is 1 inside the smaller cone and 0 outside the larger one. Well, you have to also regularize the vertex of the cone. So you need to make this. You need to get a smooth domain there so you can work in it. Okay, and so the idea is you start with just a rough approximation, and then you try to solve the you look at a perturbation problem. So you just look for your solution G bar, which is a perturbation, so G tilde plus H of the approximate solution, and so then you can write that equation as so R G bar is the background, and then there's a linear part, a linear operator, roughly the linearization at G tilde, and then there's a nonlinear term, and then you try to correct it using Picard iteration, like an inverse function type argument. So you look for a small h, which is a solution of that equation. And so, well, I've written down some of the operators here, but let me just say that, yeah, so what happens here is that you can actually solve the system where you fix the decay at infinity, and you can impose arbitrarily rapid decay of the solution near the boundary of the cone. And that's what makes it possible to get smooth solutions which do this. Okay, and so the fact that you can do that is related to the fact that the constraint equations are a very underdetermined system. So there are a lot fewer equations than unknowns, and the structure of the system plays a key role there. So I won't go through all of that, but basically that's the idea. So the problem involves solving the equation in a space with two different decay rates, two different weights. So one is a weight that forces decay at infinity, the other is a weight that forces decay near the boundary of the cone. Again, so it turns out you can do that and make it work. And so there's a key estimate. So let me just close by explaining where the restriction on the decay comes in. So the key estimate is if you look at the we look at this linear operator L tilde, so that's computed with respect to the background, the metric we constructed by patching, and then we can look at its adjoint. So the basic principle is that in order to prove that L is surjective, so L is a linear operator from some space to another space. In order to prove it's surjective, it's enough to prove the adjoint is injective. So what we need is a strong injectivity estimate on the adjoint operator. Okay, and so that's what this statement is. So it turns out that this inequality is true actually for any positive S. And so these are L2 Sobolev norms. There's no boundary condition on U, so that's actually a crucial thing. So this operator L star is a very strong operator. It's an operator that takes functions to symmetric tensors. And so it encodes roughly the Hessian of the function. And so you get a very strong injectivity radius estimate. This is true for any positive S. You can prove this in a cone. So this omega is a region which is a cone outside a compact set, and then it's some smooth region near the vertex. Some smooth region near the vertex. Okay, and so we use that injectivity, and so we have to understand. So when we're studying our operator L, we're imposing some decay on the solutions, and so if we impose decay like on our metric like x to the minus q, then when we apply L, the image will be the space that decays like x to the minus 2 minus q, decays 2 orders faster. Okay, so the range of L is H0